You have fallen into Event Horizon with John Michael Gaudier. In today's episode, John is joined by Dr. Samuel Courville. Dr. Samuel Courville is a planetary scientist whose work explores the geologic and hydrologic evolution of small worlds across the solar system. At the Planetary Science Institute, he investigates subsurface water processes, cryovolcanism, and the long-term potential for habitability on worlds once thought geologically dead. His research has revealed that Ceres, the large object in the asteroid belt, may host evidence of recent hydrothermal activity and a persistent subsurface brine reservoir, suggesting internal energy sources that could sustain habitable environments far longer than expected.
Dr. Samuel Courville, welcome back to the program.
Well, thanks for having me again.
Now, last time we discussed Ceres, but now we're moving to a different environment, one of now the three potential environments, or at least good case environments for life and abiogenesis. But here we're to Mars. And I asked you the question, follow the salt, but we also know that Mars had salt as well. Do you think that Mars is potentially a better environment for abiogenesis to have occurred than Ceres is?
Well, that's a tough question right off the bat. And, it's got to be pure speculation. In some ways, you could say yes, because it's going to be more terrestrial-like in the past. Mars's surface is most certainly more terrestrial-like than the interior of a water-rich dwarf planet or asteroid. But on the other hand, a body like Ceres has way more water and way more organic matter. So if we knew the conditions for abiogenesis, we could answer that question. So I don't have a good answer to that question. Of course, Mars has always been an exciting place for exploring astrobiology, just because it could have been so Earth-like in the past.
The Allan Hills 84001 meteorite contained sort of cracks with clays in there, indicating the action of water, which at this point, we know Mars was wet. I think it's pretty obvious at this point. But that experiment, looking at that meteorite found in Antarctica, seemed to show what might be remnants of life. What is your opinion of that research? Do you think that that's a dead end and that it's probably something geological and it's probably not worth discussing anymore? Or do you think that we should reopen that investigation and look at that again?
Oh, the former. I think right, the current investigation of the Mars space exploration program is doing the correct thing, right? We're investigating the environments. And right, if we can collect samples from the surface of Mars in these environments that we have constrained, I think it's going to be quite exciting. Now, I don't want to actually talk too much about, I think there have been a lot of recent research on Perseverance and Curiosity results, and I think you even had another speaker talk about the recent findings from the Perseverance rover. So I don't want to talk too much about that. I actually would like to talk more about our understanding of ice on Mars, where water ice is on Mars, to the best of our knowledge today. I think it's tough to say too much more about, well, I'd prefer not to talk about the Allan Hills meteorite. I think that conversation has been had to a significant extent.
Now, ice on Mars. All right. Yeah. Obviously, there's an elephant in the room. And that is Mars has polar caps, which that's CO2. But what is the ice profile at the poles of Mars as far as water? Because we sent missions that kind of looked at that. What do you think?
Yeah, so Mars has quite a bit of water for a long time, right? We wanted to just follow the water. It's not really the mantra anymore because we sort of have followed it. We know where all the water is. Mars has these nice polar ice caps, which I'll talk about a little bit more, but also it has water ice frozen in underground in the mid latitudes. So Ice itself is not stable on the surface of Mars at the equator, but as you go more towards the poles, it gets colder and ice can survive latitudes north of 60 degrees latitude. So we have these big deposits of water ice in the polar caps, and then we have more water ice that's sort of buried underground as we go towards the equator. And so there are a couple different reasons we care about it. Well, one is, what does this water ice tell us about the past climate of Mars? How did it get there? What do we know about the past climate? Was it more or less wet in the past? The process of these subsurface water ice sublimation, atmosphere, surface interchange interactions. And then the other reason we care about it is if we ever do send humans to Mars, if we ever have crewed missions to Mars, water ice is a great resource. We can use it for fuel or possibly for life support. So those are the two reasons we care about water ice on Mars.
You don't have to bring your water with you. It's already there. You don't have to launch it off the surface of the Earth.
Yeah, but it is a little bit harder to extract on Mars. But yeah, you wouldn't have to bring huge amounts with you.
Now, in regards to this ice, all right, how old are the Martian deposits of ice? For example, we take ice cores to look at, in Antarctica, to look at the history of basically that continent, since it's been icy anyway. And we're able to reconstruct climate data and all kinds of stuff from that. Can we do that with the Martian ice? Has it been sitting there locked up and layered for this whole time?
That's like the holy grail of Mars polar science research. Exactly. If we could, if we could be on the surface of the Mars polar cap, and if we could get a core, that would be amazing, right? Exactly as you said, the core samples, from Antarctica, you can see climate events in it. You can see volcanic eruptions. You can see different events throughout the history of Earth. And so, yes, absolutely, we think that there are climate events recorded in the Martian polar caps as well. And we do have snapshots of this record from orbital instruments. There are radar sounders that are orbiting Mars. One is called the Ceres instrument on board the Mars Reconnaissance Orbiter. And it's a radar sounder. It shoots radar waves at the surface of Mars and then records what reflects back. And ice is transparent to radar waves. So the radar waves go through the ice, and if there are any impurities in the ice, it reflects a little bit of the energy off of those impurities, and those are recorded back. And so these radar sounding data produce images of impurities in the ice caps, and you can see these wonderfully beautiful layers that go all the way through the ice cap that are recording something, and probably related to the depositional history of the ice cap, probably related to the climate. And we're still piecing all of that together.
Mars gives me chills for these reasons, and it does this geologically as well, because Earth is constantly recycling itself, subducting its geology and weathering and, everything changing and continents moving. And Antarctica used to have dinosaurs, and now it's frozen, all of these things. But Mars represents a much, much earlier object, a snapshot of the history of the solar system, at least, that could give us clues to what early Earth was like. And I think what's interesting is that, as you hint with the ice and the idea of ice layers, Mars seems to have swung quite a bit as far as liquid water on its surface early on. It seems to have drier periods, wetter periods, and all that, while it was losing an atmosphere, losing the bulk of its atmosphere. And I think that would be extremely interesting to have a decent profile of the history of that, because it tells you what a planetary atmosphere can really do. Do you agree?
Yeah, absolutely. I think we need to be, for example, the polar caps. We're not really sure what a record they contain, but it doesn't go back super far. It doesn't go back billions of years into when we think, there could have been a, liquid water ocean on the surface of Mars, where that has been hypothesized. The record in the polar caps is probably a bit younger. It's probably tracking how the obliquity of Mars has changed in the past tens of millions of years. And that's just because we can look at the polar caps. One of the amazing things about these radar images is you can actually kind of see instances where we think there are craters within the polar ice caps that have been covered and later covered up by more deposition. It's tough to interpret them. But so you can kind of get an idea, obviously the surface of or you can get an idea of the age of the polar caps, right, based on the abundance of impact craters and stuff like that. So these are probably recording more recent, like obliquity changes and climate variations in Mars's history. So if Mars had, more of a tilt in its past, then there would be greater temperature fluctuations at the poles throughout the year, which means ice would be stable some parts and not other times of the years. And so that would drive some of these possible layering structures in the ice cap. Similarly, ice that is beneath the surface, closer to the latitude, or closer to like the mid-latitudes of Mars, at places where ice on the surface would not be stable today, indicate that maybe ice was stable there sometime in the past. So again, we're getting a record of past climate shifts in Mars history, but not quite to the level of talking about liquid water on Mars, billions of years ago.
Now, other weird geology. I have to confess that when I was 5 years old, I saw a volcano explode, Mount St. Helens. And one of the things that did was melt the glacier on top of it, causing huge mud flows, lava flows that were extremely destructive. Ooh. Is there evidence of that kind of thing going on with Mars and its volcanoes? In other words, did these things once during this period have glaciers, and did they melt those glaciers? And is there, alluvial fan or something like that from that? Have we ever seen evidence of that?
So the volcanism on Mars is not, right? There is no Mount St. Helens on Mars. Mount St. Helens is right from the subduction of a plate, but Mars doesn't have plate tectonics that way. Instead, we get these massive shield volcanoes on Mars. So not quite the same volcanism, but you are right that if there's ice, they can certainly interact with it. Perhaps another analogy, there are some shield-like volcanoes in Iceland, again, underneath big ice caps. And so when they erupt, they can cause quite the disruption of the ice shell above. And so there has definitely been some recent research into what would happen to the atmosphere of Mars, to the content of water if these volcanoes were to erupt. So it's certainly interesting, but I don't think the picture is very clear yet. As far as features we know of today, there appear to be glacier-like flows. They don't appear to have been related to volcanism in any way, but they could be stores of water ice. They're kind of in these valleys on the edges of mesas. They're sometimes called lobate debris aprons. They look like debris-covered glaciers, so big chunks of nearly pure ice that are shielded from sublimating by being covered in debris and regolith on top. And so there are certainly features that show that there are big, thick deposits of ice across the surface of Mars. I'm not sure of any evidence of its interaction with volcanic eruptions.
Well, we have to give a very special shield volcano on Mars its due, because it is enormous Olympus Mons. Mm-hmm. Mars laughs at Earth with our Mount Everest. It's nothing compared to that. This thing is bigger than the state of Colorado, and it's a volcano that must have been active for God knows how long, and it's so big that it now basically pierces most of Mars's atmosphere at its summit. But let me ask you an off-the-wall question related to this. Do you think that the mountains of Mars. Perhaps not Olympus Mons. Maybe it was a little too hot with that caldera and everything it has. But do you think they once saw snow? You know, we know it probably had a water cycle, rain, but what about snow? Was during this period, would it have supported that?
So it already happens. There's already a cycle of CO2 deposition on the polar ice caps.
Yeah, I saw it with the Viking landers. You remember that picture where it frosted? But that's CO2. I'm more interested in the water.
Oh, certainly. Why not? Liquid waters or water snowflakes. I don't know. Maybe. Certainly could have been possible when the climate was different in Mars's past. And of course, you would totally expect it, right? That's exactly, when the environment's right. It's a natural process.
Snowfall at the poles, it's an interesting idea, because I always try to envision early Mars and see how close was this to Earth. What does early Mars look like compared to Earth now? What did it do that it no longer does that Earth does? And it sort of puts it into perspective, perhaps.
Yeah, definitely.
Now, the big question. When in our discussion about Ceres, we were talking about brine, salty water. And we know that Mars has salt. We know that it also had some brine. Is it possible that the brine persists below the surface of Mars to this day? Could it have groundwater?
Oh, man. So again, we've tried to follow the water. We're trying to understand. And so, so there's water ice on Mars today. We kind of know where it is. Fascinating for what it tells us sort of about the recent climate history. Fascinating for what it could be used for if we go there. Then, of course, there's where the Mars rovers are exploring. They're looking at places where geologic evidence of past liquid water flowing. Then we have evidence of liquid water deeper within Mars's interior in various places. So there's two fascinating possibilities. One is, well, again, you have porous rock, and if you go deep enough, the temperatures and pressure will be adequate for liquid water. And so there has been arguments that there could be an aquifer of liquid water just naturally in Mars's subsurface, kilometers down. There's been studies that have looked at the seismology data from the Mars InSight mission. This is a lander with the seismometer, measured the seismic signals to constrain the deeper interior of Mars. And although, you're mainly looking at the deeper interior, trying to figure out if there's a metal core, stuff like that, they also get properties, the seismic properties of the crust of Mars. And by constraining those properties, they find, it's not inconsistent with there being liquid water. So it's possible that there could be a liquid water reservoir deep in Mars's interior. The other tantalizing possibility is, again, back to the polar caps. Well, we know these are water ice. We know that they're water ice. But again, go to the bottom of the polar cap. The very bottom is there liquid water beneath the polar cap. This would be analogous to, the Antarctic subglacial lakes, where there's a thick ice sheet, and beneath it is, a lake of liquid water, kilometers beneath the ice. There's one location where there's a possible detection of liquid water beneath the south polar cap of Mars. Again, using this radar sounding data, radar waves go through ice. Ice is transparent to radar waves, but water is not. Water is a great reflector of radar waves. And so there's a strong reflection beneath part of the south polar ice cap that could be consistent with liquid water. If there's liquid water, though, because we know the temperature on Mars's surface, and we know how much the temperature, we know the thermal conductivity of the ice shell, we know sort of how warm the base of the ice shell could be, and it must be quite cold. So for there to be liquid water, it would have to be incredibly salty. The more salt you have it, the lower the freezing point is depressed. So there could be a salty subglacial lake beneath the south polar cap of Mars. But I think this is still a very active debate, and it could be other effects that produce this bright radar reflection beneath the south polar cap.
Can we tell how deep that is? In other words, how much drilling would we have to do to get a sample of that liquid water, if it is indeed liquid?
Ooh, I'd have to go look at the map of the exact location of the bright spot and how thick the ice cap is. It's easily Googleable. But I mean, we're talking about these are kilometers thick, so multiple kilometers you would have to drill through. So of course, this is stuff that can be done on Earth.
Oh yeah, Lake Vostok.
But we got to get all of, if we wanted to do something like that on Mars, we got to get all that equipment to Mars. And that would be, I'd love to see it happen. And you talk about the payload capacity of a, SpaceX Starship, it starts becoming more plausible. But then you got to think about, well, if you're interested in it because it's a potentially habitable environment, you also got to be careful about how you're interacting with it. So there's a bunch of fascinating questions when you start talking about exploring a place like a potentially habitable environment on the base of a Martian polar cap. And so what I would recommend, or what I would hope to see, is first new measurements, higher resolution radar, maybe some sort of lander that can better confirm the presence of liquid water before moving all the way to drilling. But it is fascinating to think about. And yeah, if we think there's liquid water in there, there's life in Lake Vostok. So,
oh, yes.
Yes, it's another fascinating possibility. But it's still at the level of it needs to be confirmed.
I would be happy right now just with a planned, being executed sample return. Get Chevet Falls rock back, take a look at it, get it down here on Earth, and
100%. It's a logical next step.
That's the next step, and a sample return. But it certainly, there's no question that Mars is not boring. Put it that way. It's actually getting, like Ceres, it's getting more interesting the more we know. Now, all right, so give us an idea about groundwater recharge and that going on with Mars early on, and what does that mean? That's part of a hydrological cycle, right?
Well, yeah, right. Right. These are fundamental processes, right? So if you do have an environment that can support liquid water, and if you have liquid water on the surface of Mars, it'll have hydrological cycles similar to Earth. Groundwater flow occurs the same way. It's the same physics. There's pressure, there's pore space, and there's fluid, and the fluid moves from high to low pressure. An interesting consequence of Mars's topography, Mars has a topographic dichotomy. The north hemisphere of Mars is all lowlands. The southern hemisphere of Mars is all highlands. So, the terrain is just much higher on the southern half of Mars. So if there was water, and if it was distributed on the southern hemisphere, it would want to flow towards the northern hemisphere. So there have been studies that look at the possible groundwater flow that you might expect on an ancient Mars. And then, of course, when you look at the surface of Mars, you see all these outflow channels. You see these channels, if you look at Valles Marineris, you can look at the surface of Mars and you can follow these channels. And some look more or less like fluid flow channels. Some look massive. Some seem to appear out of nowhere. But they're sort of, all originating on the dichotomy boundary near Valles Marineris. And so you can speculate about how maybe groundwater flow, the hydrological cycle, would play a role in developing these features, how long-lived they were and whatnot. And those are all goals of understanding the past environment on Mars.
I love the naming scheme that was used for Mars, where Valles Marineris is, the valleys of Mariner. They're very, very almost science fiction type names. They're just so good. Or Utopia, Planitia, and things like that. What do you think? All right, follow the water. Let's say follow the ice first. What is the next step logically to investigate the ice, the water ice specifically of Mars? What can we do mission-wise to further that research? Because that's, we got the radar and the seismic stuff, but there's got to be more that we could do to get a profile of that ice. What would you do as a scientist?
Yeah, so it all depends on your goals. If your goal is, one of the important goals is just understanding where it is, how much of it, and where it is. It's a little bit more, it's easy to do that on the polar caps, where the radar data can constrain the thickness and the extent of the ice. But for ice that's mixed in with regolith, a little bit deeper beneath rock, it gets harder. The resolution of the radar instruments for the near subsurface of Mars is only, it's 10 meters. So, if there is water ice in the first couple meters of the subsurface of Mars, and then it's sort of maybe mixed in and goes deeper, or maybe it's, there's some thin layer, like some of the exposed icy scarps that we've seen towards the mid-latitudes of Mars, or if it's in the form that we discovered when the Viking lander the Phoenix lander took a scoop. We're not really going to be able to see it with our current radar instruments. We need something that's a little bit finer resolution. And so one of the more easy things to do in the near term is a new orbiter with a higher resolution radar designed for mapping where ice is in the near surface of Mars. And again, one of the big drivers for this is figuring out just where the ice is, how much of it is, because for future exploration of Mars. If we want to send humans there, if we think we're going to need to use water ice, we're going to want to land somewhere where we think there's water ice. And so right now we can't quite constrain it with 100% precision. So that's one of the first things. It'll be another surveying mission to figure out the abundance and distribution of near surface water ice. So there have been some concepts and plans for possibly putting that together. An interesting thing when we think about sending humans to Mars that may need to use this water ice is there's sort of a limit to where missions can land. You can't land everywhere on Mars. For example, you couldn't land on the top of Olympus Mons. It's so high that there's no atmosphere to slow you down. So you couldn't use a parachute. You couldn't slow down. You just crash into the volcano. So there's sort of this elevation cutoff where you can only land at terrain that's low enough elevation that there's enough atmosphere to slow you down, at least with our current landing technology. So what we're looking for is overlap between where there's ice in the subsurface and where are good landing spots.
You would expect, though, that Olympus Mons, if you could land there, say, let's rephrase it. We shoot an impactor at it and look and see what comes out, or something like that. But it's all going to be basalt, wouldn't you think? There's probably not the place to look for ice, I would imagine. Is that correct? Avoid the volcanoes. You don't need them anyway.
Oh, yeah. That was just an example of high topography. But again, it all depends on what your goals are. One other fun goal is lava tube exploration.
Ooh.
There are hypotheses that lava tubes on Mars, because Mars is smaller and the gravity is less, lava tubes could be a lot larger on Mars, right? These are the, sort of like caves that are developed by the flow of lava as they sort of encase, as the lava flows and solidifies, and it sort of encases itself, and then there's a tube of lava as it flows, and then eventually it all solidifies, but the tube stays behind. And so there's evidence of, they're called skylights, where you can see where a lava tube has collapsed, and you can look in and see a depression. Lava tubes are another fascinating geological feature. They're scientifically interested, but also another possible human exploration target, because that's like a natural shield if you could live within these tubes.
Yeah, you don't need a dome, just build it in the tube. And that actually works for other bodies too, because we see the same features with the moon, for example, extinct lava tubes.
And they could be even larger on the moon.
They could be. And the one place in the solar system that sort of freaks me out, Io, probably has
Oh,
them,
yeah.
you know. What a weird object that is. Io is everybody's focuses on Europa. Yeah, liquid water, ocean, whatever. Sorry. But the Io fascinates me because what happened there? That too had water, probably, when it formed. What might have happened there with water and volcanism and, all the things that might have happened there.
Uh-huh.
And I don't know that enough attention has been paid to that object.
We're digressing from Mars, but there have been many proposals for missions there. And, one day one will stick.
One day. Now, Earth has had episodes of climate swings. Most famously are the ice ages, but it apparently could have been much worse. The snowball Earth hypothesis and things like that, where everything almost completely froze over, shows you the dynamics of a planet that's going through changes. Is there any evidence of that for Mars, above and beyond anything else? Does it look like there was glaciation there of a large scale, or is its history just so different from Earth that it never saw that? It never saw the huge ice ages that we saw?
Well, again, right, like the surface of Mars it's pretty old, right? There's lots, especially you just look at the number of craters in the southern hemisphere. So there haven't been active processes to resurface Mars. But again, we can look at features that, still exist today. There are these debris-covered glaciers, what we think are debris-covered glaciers that still exist today. There are all these channels of liquid water flowing. I don't believe there's clear evidence of like massive like glaciers like you imagine them, in pictures of Alaska, where you see these glaciers carving mountains. Those don't so much exist. But as I said, there are these debris-covered glaciers and stuff like that. But again, there's no, how do I describe it? The surface of Mars is old. It hasn't been resurfaced. There's not like a cycle of these processes. It's almost as if there was one period in time where it occurred, and then it's been dry since.
Atmosphere loss. Does the evidence from the ice or the rock tell us when the period ended for liquid water on Mars? In other words, too much atmosphere was gone. No more liquid water on the surface of Mars. Is that evidence preserved geologically or hydrologically, I guess would be the way to say it?
Ooh, good question. I do not know. So I know there's been a dedicated mission to study atmospheric loss at Mars, the MAVEN mission. No, I don't know. I mean, I think just constraining the past atmosphere of Mars itself is a huge goal. And, it's something that collecting samples is going to help with. If you could unlock some of the history in the polar caps, you'd at least get some of the near-term variation, the past tens of millions of years. But no, I do not know if that's well constrained at the time.
Just shows how much we don't know yet about Mars,
It's tough. I mean, it's hard. You're talking about stuff that happened billions of years ago. And even though Mars hasn't had its surface erased, it's a tough question to answer. But that's why it makes it better to answer, it's something that you can at least look, there's evidence of it still on Mars, whereas on Earth, you got to go to special places to find rocks that are that old.
Yeah, but eventually you get to the point, even when you are exploring Mars, you have to go to special places on Mars. Mm-hmm. And we're nowhere near that. There is nothing but centuries.
We're already going to special places, right?
Well, Gale Crater, yeah,
sure. Gale Crater.
Yeah.
They're special places.
But even when you're in a not so special place, like the Vikings, there was still interesting stuff.
Oh, yeah, definitely. Yeah.
It's tempting to take too broad of a view of Mars and say, oh, it's all, no, it's not. And one of the things that always fired my imagination is that we land in the safe spaces, right? We go to the places that, like you were saying, we're very choosy about that. And you don't want to go. I doubt we would even put a mission where the Vikings landed because of all of those rocks everywhere that could tip your spacecraft over and all that. I doubt we would do that again. But imagine being able to stand at and like look at Valles Marineris and see the vista like the Grand Canyon. And what would that look like?
I wish there was another class of missions purely developed to take pretty photos, because that is another photo that I would love to have, a vista of Valles Marineris.
I'm trying to get the billionaires to say, hey, I can make money off taking pictures of that stuff, so I'm going to finance a camera and put it right on the edge of that that canyon, because it is by far the largest canyon in the solar system, and I don't think we even know how it formed. I mean, that's the weird thing, is we don't really even know why that's there.
No, I mean, you can spend hours just looking at the topographic maps, the spectral maps, just the images of it, and and you just look at it and you see more and more interesting features. You see that, yes, there's Valles Marineris there, but then you look a little bit north of it and there's these just big depressions. Of course, these themselves are massive canyons, and they seem to appear out of nowhere. And then if you go a little bit to the west, you just see this chaotic terrain of hatchwork of different cracks in Mars's crust. And presumably they're all tectonic in nature, some sort of spreading. So, like, could it have been the start of something like plate tectonics as we know it? And then at the same time, you have evidence of flows sort of originating from the east side, as if water somehow was coming out. So yeah, no, it's just more and more fascinating the more and more you look at it, and the more and more unsolved it becomes in your head.
Yeah, and it's like regarding plate tectonics, I mean, that question is so deep with Earth that it may actually have played into habitability. That carbon cycle that happens and all the stuff that goes with plate tectonics here. Whereas Mars looks in some ways like the egg almost cracked, but not quite. And that left it with this weird geology where you've got these huge escarpments and things like that we don't really see with Earth. And I find that equally fascinating, I think.
Yeah, I 100% agree.
Now, what is the future for ice mapping? And tell us about the SWIM project.
Yeah, so I talked about it a little bit, right? The goal is really just to figure out where and how much ice there is. So I'm going to switch, I've been dancing around going from, scientific interests to human exploration interests. They can kind of go hand in hand, right? One of the reasons we'd send humans to Mars is to do more scientific investigations. There are certain things that a human can do way better than a rover or a robot. But as far as sending humans to Mars, in situ resource utilization, if we need water there, one of the best ways to get it is just from water ice. Now, if you're going to make a mission and you're saying that you need water ice, you better be damn sure that there is some water ice there. You need to have a proven resource of water ice. And so that comes along with a lot of things. You actually need to make sure it's possible. Like, okay, if there's water ice there, can I extract it and can I use it? Can I melt it? That's a challenging engineering problem on its own that's under lots of research. I am focused on quantifying the abundance of water ice. So how would you know if there's water ice in the regolith or a little bit beneath the regolith on the surface of Mars? You can't see it with the images. Again, this gets back to things like radar. If there's ice in the regolith, that changes how reflective ground is to the radar. So that's one way to quantify it. But it turns out having ice in the pore space in the regolith doesn't look all that much different from having nothing in the pore space. So the radar can't do a good job of distinguishing if it's ice or nothing. So it can tell you if it's porous. It can't really tell you what's in the porosity. So then we got to start looking, what other data do we have? We have the neutron spectrometer. the Mars Odyssey neutron spectrometer, named MONS. That one can tell us about the abundance of hydrogen in the near surface of Mars. It can only really see the first, maybe centimeters of the surface, but it can tell us about how much hydrogen is present. Hydrogen, of course, a key component of water, H2O, it's not in most silicate rocks. The way to have hydrogen in the near surface is either in ice or in hydrated minerals. If it's ice, you can hold a lot more hydrogen. If it's hydrated minerals, then it's something like maybe 10% by equivalent mass of water. So by making these maps of the hydrogen abundance in the near surface, that tells us where there's either some ice or some hydrated minerals. So that's constraining our parameter space a little bit more. It has a really coarse resolution though. We're talking about like tens, hundreds of kilometers per pixel. And then we have thermal imaging. If you have a dusty regolith, things like thermal imaging can tell us how quickly the surface is radiating heat away. We call it thermal inertia. A rock has high thermal inertia. When you go touch concrete, even after the sun has gone down, the concrete will still be warm. It has high thermal inertia, it holds its heat well. But dust, sand, not so much. It'll be cooled down. So that's why you can have colder sand next to a hot rock on a beach, even after the sun has gone down. Same thing happens on Mars. Ice tends to favor the higher thermal inertia ends of things. So if you observe the ground of Mars has a higher thermal inertia, that's more consistent with ice being in the subsurface regolith than just being empty regolith. Okay, so those ingredients there, we've got these three data sets. When you piece them together, when you interpret them jointly together, now you can start picking away and figuring out when they are all consistent with ice or not. And so that's the crux of this subsurface water ice mapping project, is bringing together all of these data sets to constrain as much as possible the existence of ice. The future is taking it one step further and putting a number on it. So not just saying, oh, these data sets are consistent with ice, but saying these data sets are consistent with this much ice at this depth. Because now, with that information, you can start actually talk about a resource being available for human exploration.
So my last question for you is this. If given the chance, and my answer to this would be absolutely not. I'm not leaving this planet under any circumstances. But if given the chance and the funding to go and study that ice in situ, would you go to Mars?
It's funny. I ask these questions to a lot of my colleagues. Most of the time the answer is no. For me, it's an absolute yes. I absolutely would. I'm not sure I can say why, other than just I couldn't imagine.
Overwhelming curiosity, perhaps?
Yeah, exactly. So yeah, 100% yes.
I've always noticed that there are these people on Earth that are like me that don't even, I wouldn't even go out into the, like Point Nemo out in the Pacific. I wouldn't even do that. But then you have also people that will climb Mount Everest because it's there.
Yes, it's there.
And I think that the people that will climb because it's there, and I think that, if space tourism can get going and private colonization of Mars, you end up with a certain class of people, a certain type that will go there just because, even if it kills them. And we're on the cusp of that. But do you think that it's dangerous? In other words, if there's life there?
Yeah, 100.
I mean, not dangerous. Well, we know it's dangerous anyway. But if there's life there, do you think that we should perhaps quarantine Mars until we know more? And we need to look at that water. We need to look and see if there were or are microbes there 100%. And what those can do.
Yes.
So do you think we should just put the brakes on going to Mars too fast?
Well, first off, it's tough to get everyone on board with that, right? We have to decide what the risk is and advocate, because there are people who are going full steam ahead, right? Let's get people on Mars. But at the same time, there is a ton of research into planetary protection, which goes both ways. We want to be careful about what we send to Mars, and we want to be careful about what we bring back. I would say, right, again, it's tough. We don't have any confirmed evidence of life on Mars. But if there is, yeah, you could certainly mess with it. Or if the environment on Mars is habitable, you could easily bring Earth life like there and have it survive. So we need to be careful when we investigate these potentially habitable environments, that we're not contaminating it, altering it, or right, contaminating the very evidence that we're trying to explore. Yeah, I think, I have recently learned to scuba dive, and it is fascinating being in an environment that humans are so clearly not meant to be in. And so, right, go to Mars because it's there, but also it's just like being able to see something that you are not supposed to see. So there's just a natural curiosity to see it. There's ethical dilemmas. So all of this needs to be discussed and decided upon by the community. And I hope that we develop the right tools to investigate it responsibly in the future.
Well, once again, you triggered the science fiction author, and here is my final thought. What about if you see life you're not supposed to see? In other words, a dying planet like Mars, as it very slowly died, and evolution adjusted to that and created a microbe, perhaps of the opposite chirality, which carries a lot of weight, when dealing with, because, the human immune system cannot fight an opposite chiral organism, and that Mars could be deadly to land on, and that we need to be very careful. The only saving grace being that Mars has been sneezing on Earth for its entire history, and we're okay, with the meteorites, but it's very scary if you think about it, that a very generalized bacterium that can eat whatever it finds, opposite chirality, we might be wide open, so be careful what you do on Mars. Your thoughts on my sci-fi author, apocalyptic Andromeda strain comment?
No, it's very much real concerns, right? There are protocols for if we ever bring the samples back that Perseverance have taken. There's protocols to ensure that we handle them safely. I personally, I don't know if this is pessimism on, as a scientist, I have a bias to be more skeptical. So I'm almost sort of biased against life on Mars because I need extraordinary evidence to prove that there's life there. And so that bias sort of conversely picks up in this debate. And I think, nah, that's not that plausible that there would be dangerous life on Mars. I'm so skeptical that there's life on Mars as is. But you're absolutely right that it is definitely something on the radar of scientists and engineers and ethicists when considering bringing stuff back from Mars. If you go to Mars, if humans get to Mars, and then, presumably they want to come back. So we better be sure in advance that it's safe for them to go and come back.
I think it would be prudent. Thank you, Doctor. And
that's another reason to have sample returns.
Well, yes, and it's also a good reason to bring Lysol with you if you go to Mars, in case you have to sterilize all the rocks around you. Although I imagine the perchlorates are probably doing a pretty good job of that. Especially if there's any kind of water there. So you might have your own Lysol on that planet. Yeah. Thank you for joining us today, Doctor. And I look forward to further papers on the ices of Ceres and Mars. And a lot of ice out there. Yeah. A lot of ice. You're never going to run out of ices to study in this in this star system. You're never going to be out of work.
Yeah, 100%.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.